Hello. In this video, I'm going to talk about slack variables and the pivot. So, in chapter 3, we looked at maximization of linear programming problems, and we were always given an objective function. So, just to recap, we have that you're given an objective function, and then you're given a set of constraints. And then this right here, this represents that you're restricted to quadrant 1. Now, whenever we try to maximize a objective function using a set of constraints, we need to make sure that they're in standard maximization form. So what you're going to be looking at in your examples is that basically you have that you'll have something like ax1 plus maybe like a1, yeah, and then maybe like a2x2 followed by like an xn, and then you have that this is less than or equal to b. So standard maximization form has that all of the constraints are of this form. Now, the other is that you have that you're maximizing some type of objective function. Okay. Now, of course, the remaining things is that of your uh, all of your variables like x1, x2, x3, and so on, all of those must be non-negative. So whenever you have a word problem, just make sure that you make all of the variables non-negative. Now, it gets a little interesting in terms of like, okay, well, what exactly is a slack variable? So let's go ahead and say that, we go ahead and introduce what is called slack variables. So the first step that you would need to do is that you would need to basically just rewrite your equations as 3x1 negative 2x2 plus 2x2 plus 4x2. Now here's where it gets interesting. I'm going to add a variable that I call s1, and then I'm going to add a variable that I call s2, and then we're going to say that this is equal to 12 and this is equal to 8. Now, basically what happened is that for each of the constraints, I had to add a slack variable. So every constraint has to have a slack variable. So if there were 3 constraints, there would be 3 slack variables, one for each constraint. If you want to label this as, equation or inequality 1, inequality 2, that way you can keep track of how many slack variables do you have. So just know that, yeah, a slack variable basically has that, you know, S1 and S2 in this case, they both have to be non-negative as well because of the fact that all variables must be non-negative. Now, the thing about these slack variables is that they must be they they have to take up the slack for insurance of like equality. So for instance, um, if we have that like x1 was equal to 0, and if we have that, let's say that x2, um, let's say that x2 was equal to 2. Well, notice that in the first equation that you would have 2 times 2, which is 4, but that's going to be 8. So that means that S1 has to be 8. Why? Because you have 2 times 2 is 4, plus the 8 gives you 12. Now in this case, note that basically if x2 is 2, you get 8. But over here, you have 0. And over here, you have that well, you have an 8 over here. So in that case, that means that S2 would have to equal to 0. Now, basically, we call these the basic solutions. But basic solutions may not be the most optimal solution. Okay, so that's just one thing that you just have to remember is that not all basic solutions are the optimal solution, and we'll kind of see like what that means. Okay, so I've introduced my select variables to each constraint. Now, here's where we need to add in more information. So notice that we have an objective function that says 2x1 plus 5x2 is equal to z. Now the thing that I need to do with the objective function is I need to convert it also to a linear equation, but I need to do it in a way that it has all variables on one side. So we're just going to write negative 2x1 minus 5x2, and then we'll just put plus z equals to 0. Now in actuality, this is more like a third equation. Okay, so just to recap, all I did was I just rewrote the objective function as a linear equation. Now, notice that here you have that there are a few variables that we can tabulate. So the next step that you would do is that you would actually introduce what is called the simplex tableau. Now, a simplex tableau is essentially a table of which that you're just kind of just accounting for all of the variables. So more or less, I'm just going to say that it's kind of like a matrix. So we draw essentially a matrix where we have to account for all of the coefficients of our tableau. So we have x1, we have x2, we have s1, we have s2, and then we have our constant that we'll just call, oh, no, we have z, and then we have b. Okay, yeah. And then we can just go ahead and close this. And then I'm going to go ahead and just draw a line along here. This is to separate the constraints from the objective function. And then I'm going to draw a line right here to represent the equal sign. Okay, so again, basically all that we're doing is we're just accounting for the coefficients of your equations. So you have 3, negative 2, negative 2. You have 2, 4, and then you have negative 5, and then you have 1, 0, 0. Now, the zeros are because there's no 0, or there's no S1 for equation 2 and for equation 3. Followed by 0, 1, 0, 0, 0, 1, and then you have 12, 8, and then 0. Now, right now, you have that this is what I call the initial simplex tableau. So just to be a bit more, specific, so we're just going to say that this right here is what we call the initial simplex tableau. Okay, now what we have from here is that some of these well, we do have that there is a solution right now as we look at this. So right now you have that there is no optimal value, it's 0. But to kind of understand what's going on, right now we have that x1 is 0. The reason that you have that x1 is 0 is because of the fact that you have that there's kind of like there's we're going to say it like this. You have to have that there's a pivot. So there is no pivot in x1. There is no pivot in x2. So what a pivot means is that you have that there's an entry that is like a 1, so kind of like this right over here, followed by some zeros. So you have to have that, like for example, if this was a 0, that was a 0, then x1 would be equal to 4, because right there, that would be the pivot. So essentially, you want to go from what we call non-basic to basic. So this right here has that x1 is 0, and then x2 is also 0. But then you have that s1, there is a pivot, so you have that it's going to be equal to 12. And see like how s1 is basically picking up the slack because of the fact that x1 and x2 fail to be anything, so they're just 0, and then this means that that's going to be 12. Now we can also do s2, which is equal to 8. And that's again because you have that x1 and x2 are both 0, so then that means that it becomes 8. Now z, unfortunately z is just 0. Why? Because x1 and x2 are both 0. So, okay, so right now these are the basic solutions, but they're not the optimal solution. So I'm just going to put like right here that we have that this terminology for x1 is that it's non-basic because there's no pivot. So whenever something's non-basic, you have that it's just 0, or whenever there's no pivot, if you want to look at it like that. So this one right here is also non-basic. And then here, these are basic, basic, and basic. But note that this is not optimal. You don't want this to be, your goal is to maximize, so why would you, take 0? Especially if you have that you're trying to maximize profit, well, there's no profit, so how can there be a profit? Okay, now what I'm going to do is I'm going to rewrite this matrix right here. So let's go ahead and copy our tableau. Okay, so let me just copy this. And then I'm going to go ahead and just move it down over here. Okay, that's good enough. Okay, now here's where we introduce what we're gonna do. Like, okay, so you might want to know, like, okay, well, how do I solve this then? So the next step is that we need to look at the pivot. Okay, so I explained that a pivot is basically just whenever you have a constant, one of the entries is non-zero, and then followed by 0 entries, whether it's above or below. So because you see like over here, you have a constant, non-zero constant, followed by a 0 above or below. So essentially you just need to have that it's above or below. Now we need to pivot, we need to find our pivots and then find the optimal solution. But before we get there, the thing about the pivots is that it's almost exactly like finding the row operations. So you can actually switch any row that you want. You can also multiply a row by a constant. Now, the other is that, okay, now I should be careful. When you multiply by a constant, you want to do that in a way that it keeps this positive because you never want to multiply by a negative value. Um, so in a sense, this is kind of like a restricted form of row operations. Now the other is that you can multiply by a constant and add to a row. Now note that basically whenever you're looking at pivoting, your pivot operations will always involve what is called the pivot row. Okay, so there's a lot that I'm throwing out here, I know, but I'm about to like make it a little simple. So the first step is that you need to find the pivot element. The pivot element is determined by the most negative number down over here. So these are called indicators, and what you want to do is just find the most negative indicator. So the most negative indicator is right over here. So we have that this is going to be what I call the pivot column. Now the next step is to find the pivot row. So to find the pivot row, basically you're going to go ahead and divide the corresponding values in the column over here into B. So you have 6 and then you have 2. Now the key is that you want to basically find the smallest quotient. So the one that has the smallest quotient, is the one that appears right here. So we found basically our pivot element. So this is the pivot element right here. But if you want to be a bit more specific, this right here in the second row, this is your pivot row. Okay, now the next goal is to basically just make this a 0 underneath it and a 0 above it. So let's say that, for example, that we go ahead and we try to get the -5 to be a 0. So to do that, we just have to think like, what can we multiply this row by, and then this row, so that it cancels out. Now, what we can do here is just say, let's just multiply by 5 for row 2, and then let's just multiply by 4 for row 3, and we're going to make that a new row 3. Okay, now basically what's going to happen is that we're going to have essentially the same we're going to have the same second row, so -2, 4, 0, 1, 0, and 8. And we still have the top row because we didn't change anything. Okay, now when you multiply by 5, you get -10, and then you get -8, so that's going to be -18. Okay, now the next step that you would do is that you would say that you get a 0 here, and then you get another 0 because you have two zeros. Over here you have that that's going to be a 5, and then over here you have that that's going to be a 4, followed by 40. Okay, so we have 40. Now, this is not the optimal solution. The reason that it's not the optimal solution is because you still have a negative indicator down over here. So we have that this doesn't work, and we still have to pivot over here too anyways. But I was just going to add that in there, that you don't, yeah, you're not done. So we need another pivot operation to get this one right over here to be a 0. So just go ahead and say multiply by 2 row 1 and then minus, yeah, we could just say minus row 2 and then just give it a new row 1. Okay, so essentially we just need to go ahead and just get this row, and let's go ahead and just copy, and then we'll just go ahead and just go ahead and edit some things. Okay, so we just need to edit the top row. Okay. Oh, and let's go ahead and get rid of this right here. Okay, so you have that your next entry is 2 times 3, which is 6. Minus minus, that's going to be 8. So we have 8. That's going to be a 0 because of the fact that we said 2 minus 4. So the next entry is going to be a 2 because you have that, that's just 2 and 0. The next is going to be a negative 1. And the next entry is going to be a 0. And the next entry is 24 minus 8 is 16. So this gives us that we have, so right now it's telling us that the most optimal solution is 10 because you have 4 into 40 is 10. So we have that this is not the optimal solution because we have to pivot again. So we go ahead and we look at this. So right now, okay, so yeah, let me just go ahead and say that, right now x1 is equal to 0, x2 is equal to 2, s1 is equal to 8, and s2 is equal to 0. And then you have that z is equal to, well, you have 4z equals to 40, so that means that it's equal to 10. But this is not the optimal solution because you have that there's still a negative indicator. Okay, now the next step is that we repeat the whole process. So we repeat the whole process because of the fact that we have that there's the negative indicator right here. Now, interestingly enough, when we go ahead and we form the quotient, we have to pick the one that's the smallest, but also positive. So in that case, we know that, when you do the division, you get 2 and you get negative 4, but you have to use the most, uh, the smallest quotient that's positive. So in this case, we already automatically know that the pivot row is right here. So that means that the pivot element is the 8. Now, in that case, this is going to be such that we can probably just go ahead and say, for instance, like what we can multiply 8 by and row 2 by. So for instance, let's go ahead and look at the bottom second row. So I know that the row operation is going to be row 1 plus 4 times row 2 to give us a new row 2. But let's think about this. What we can probably do is just say that we'll do another row operation. So we'll say 9 times row 1 plus 4 times row 3, and then this is going to give us a new row 3. Okay, so let's go ahead and kind of like paste the new, or just start creating our new tableau. So we know that this is going to be new. We're going to get a new row 3, and we're going to get a new row 2. But we want to do this in a way that, oh, actually this whole row is different. Yeah, okay. And let's go ahead and close this. Okay, so let's, oops. Okay. Now, we know that the top row is going to stay the same, so in that case we have 8, 0, 2, -1. Actually, let's do this a little better, because yeah, we have 16, we have 0, -1, 2, and then we have 0. Okay, so the easy one is that you have a 0 right there, and then you have that this is going to be 16, so we have 16, and then we have another 2, and then it looks like we have a 3, so like we have 4 minus 1, which is just 3, and then this is going to be 0. Now this is 32. This is 32 plus 16, which is 48. Okay, so that gives us that, well, let's see what we get actually. Okay, so now we have 9 times 8, which is 72. Then we have 4 times -18, which is 72. So that's going to be 0. The next is going to be another 0. The next is going to be 18. So we have 18. The next is going to be 20 minus 9, which is just going to be 20 minus 9, which is 11. Now, this one's actually going to be just 16, so we have 16. And I did that fast because 0 plus 4 times 4, which is 16. Okay, so now we have 9 times 16. So 9 times 16 is 144. And then we have that 4 times 40 is 160. Okay, so this is going to be 40304. Okay, so we're just going to put 304 right here. Now, the thing that we will look at just really quickly is that we want to look for no negative indicators. So we have that there are no negative indicators. Now, what that means is that you can actually label this as the final tableau. And again, that's because of the fact that there's no more negative indicators. Now, the next step is reading the solution from the tableau. So you have that, okay, so we have that there's basic solution. So you have that there's 8x1 equals to 16, which basically gives you that x1 is equal to 2. And then you have that there's 16x2, which is equal to 48, which that tells you that x2 is equal to 3. Now, we have that basically that s1 is equal to 0. Why? Because it's non-basic. We have that s2 is also equal to 0. Why? Because it's non-basic. And then we have that z. This is where I was like, is this correct? But I went ahead and did the division. So 304 divided by 16 is 19. So we have that the solution is that z is the most largest value. So we'll just say that the optimal value is 19. Now, in a way, we can say that this is the maximum. Okay, so we have that our solution is essentially 19 with those conditions that you have that this also. Now, if you go back and you kind of look at uh, the very beginning, you have that you can actually just plug in those values back into here. So 2 times 2 is 4, plus 5 times 3 is 15, which is 19. So that gives you it gives you an optimal value of 19. Now, the things that you can take away from this is that you could have, for instance, you could have introduced a pivot of where you have 1, but the problem with that is that you end up with fractions. Now, if you're okay with fractions, then go ahead and do that because it's only in pairs. So um, if you do want to introduce the fraction, like over here, you could have divided by 4, and then you have negative 1/2, and then you have 0, you have 1/4, you have 0, and then you have 2. So here you only ended up with just 2 fractions. It actually does make it a lot simpler in the sense that, I didn't have to think of what was the least common multiple between 4 and 5, which is 20, versus like back over here where I had to use the what was the least common multiple between 8 and 18. It's 72. That's how I knew that I just take 9 times 8, which is 72, and then 4 times 18, which is also 72. Now you can use your calculator though, like as it relates to, how do you find least common multiples. Um, but some cases, most people think or say that, it's a lot easier just to go ahead and introduce a pivot element of 1. Now, what I went ahead and I did was I graphed this in the x and y plane. So as long as you have a maximization problem that's in the form of two variables, so like you can actually go ahead and check your work if you change it to x and y. And then the other one was negative 2x plus 4y is less than or equal to 8. And then you had x and y were non-negative. Now, the way in which that I would look at this is that, I would just plot both of these two inequalities in the x and y plane, which that's what I did over here. So essentially we have that these points right here, these are your corner points, and also 0, because you have 0, 0. So notice that basically the largest optimal value has to be the one that appears the furthest away from the origin, which in this case was 2, 3. But you can also just plug in 0, 2, 2, 3, and then 4, 0 into the objective function and see which one gives you the largest optimal value. Unfortunately, this only works for two variables, so you'll probably see that uh, the problems that you'll be working on, that it won't have two variables, it might have three variables, four variables, and so on. So that's the whole point of simplex method, which that's this whole thing about slack variables and pivots. So slack variables and pivots are only used for whenever you have like more than two variables essentially, but we use two variables for the first few examples just so that you can understand how to use it. So you're going to notice that a few problems might be repetitive, that you might see problems that you did solve using a graphing calculator or Desmos, or even just like drawing it using the feasible region. But essentially, it's because, we want you to learn how to take a different approach, essentially, using what is called the simplex method.